forward. This session is not a session in like even less traditional sense than what I came prepared with in the first 2 sessions. This is a minute for us to just kind of complain together. And
on video?
Yeah. And explore together. We'll figure it out. So, so what is the session? This title? It's like basically middle school math just got way harder.
Just got way harder.
Yeah, it's difficult. It's not hard. This is hard.
That's the first thing I said when I read it. I was like, no.
You know, that's interesting.
Hard is a physical attribute.
Yeah. It's difficult.
Well, that's
what I tell my
you guys are nerds, or is it geeks, which is more accurate here?
I'm a geeky nerd.
I think that the middle school standards got clearly more difficult and not harder. They changed an awful lot, and there's a really valid complaint that I've heard, which is, and it's too much to get done.
And what I keep saying is, yes, for a couple years. But when we start getting the kids who had the more difficult elementary standards as well, it's not going to be as much work as it is right now. And we just got to get to that.
But some of the stuff, their brains aren't developmentally appropriate for, and we're starting them off sooner and sooner. And, I mean, some of the abstract thinking that they are required to do is just, I mean... So, I mean, that was just...
In middle school?
I teach 6th, 7th, and 8th grade.
Yeah.
So I blend a lot of things together because since I'm teaching all 3 grades, I teach 6th graders like I'm going to be teaching my 7th graders, so they may get a prerequisite of what they're getting in 7th grade and so my kids got an advantage in that aspect because they get me 3 times, and I'm looking, but it's not because I also have special ed kids. They need it 3 times, you know, so they kind of need to know what they're going to be expecting in 7th grade, you know, and so like that. 6th and 8th grade, I've been pretty happy with if we had a couple more weeks before we started testing instead of just 1 more week.
Yeah, right.
I would have been okay with what I had to teach.
Yeah.
My 7th graders, I am nowhere near where they need to be for me to be confident that even if they didn't pass, that I've touched everything, but nothing that's given them anything to practice. I mean, or some things not. And then Friday I was sitting there going, okay, I have 1 week. 1 week. What do I do? What's going to be the most valuable this week? You know, what skill or
where they just get to math.
Yeah. I mean, I'm just like,
because if they math, the test will come.
So I hear you. So I think 6th grade's harder than 7th, but I could be wrong. I'm not teaching these things right now.
6th is impossible. Yeah. That's why I'm losing both of my 6th grade teachers because they're done. They're burned them out.
So 2 things that we take into consideration. So 1, our standards are still easier than every single other state's standards, and this is on record. I'll say.
Yes.
It's getting closer.
We're closer.
Cool.
In the same way that other folks have concerns about developmental appropriate issues, we have in Oklahoma, and that's really part of what killed Common Core. Well, really politics did, but from the teacher's perspective, it was a question of, can students handle this? And what we've found is yes. Yes, they can. We haven't had a system in Oklahoma where we've believed from an early grade that they should be exploring mathematics in a meaningful way, but instead they should be parroting and memorizing. So what that means is that our kids, it may be developmentally appropriate, but our kids aren't on the track.
Yeah. Okay.
Yeah.
I agree with that.
I try to make a distinction between...
If they had started out there, then yes.
So the skills are developmentally appropriate for these kids. Our kids aren't on grade level.
Yeah.
They haven't been developed appropriately.
Developmentally readily and
that's
appropriate.
That's the point that I like, this distinction. The kids haven't been developed appropriately. Let's say that for a second, which is on our system too, importantly. So what do I think these standards are meant to be? How are they meant to be taught? Um, absolutely, without a doubt, not in isolation.
Right.
A single objective in our standards that gets taught by itself has missed the biggest point that we tried to do when we set out to do the standards too easily. So I thought I'd just like play, for a minute. Let's just play. I have a math problem that's on my mind, and I just want to see how we handle it. Okay, you guys ready? That's kind of the excitement. So I've got a robot here, and this robot is going to go on a journey. And it's a pretty easy journey. You'll see. It's a square right there. Okay, the full square. It's got a start and end. But right when he gets to this corner here, he actually has to do a circle. Does everybody see that circle? So my question is, how far is his journey? And you don't get any other information. But I need not just this answer, but I need a good way to see if it's right. So we got to do some calculations here. So what I want you to do is on your own, write down a quick list. What do you notice and what do you wonder? To try to answer this question. How far is this robot going to have to travel if that's his journey? By yourself for a second.
You want the questions that we would ask you so that we would be able to figure out the
Perhaps. Mm-hmm. That's a good way to approach it.
It's like the peanut butter and jelly sandwich thing. If we don't ask them.
It's kind of the order of things, huh? Okay, so I'm seeing some ideas. We're a small group, so I want to kind of move us through these things. But in a classroom, there's something that I absolutely necessarily do whenever this happens. So we do my noticing and wondering first, and I make sure to walk around the room, and I'm going to call on students who I will have prepped. I would say, would you mind sharing this in a moment? Would you mind sharing this in a moment? And would you do this? And I'll have 2 or 3 of them. And I've thought about the order in which they're going to share. Okay? That's really important. I need kids who have something that's rather sophisticated. I can't have those things be first because then other kids will shut down. Right? Now I saw what you guys wrote, and it's pretty straightforward. So I just want to kind of hop to another point here. I can't give you a lot of what you want to know, but it is a square. It is a circle, and my question still is, how far is the journey? And there's one thing that I do know. Actually, that the distance across this circle, right, is the same as the distance halfway across the square. So, that's nice. We'll just call that A for now. So, I'd like for you to take a first draft at it. First draft. You only get
Are you asking for the exact amount or the...
either or. First draft. See what you can do to try to make sense of this.
You said it was square.
Mm-hmm.
Students would do it differently, I think.
Well, do it a student way too, Donna, if you want to.
And I'm just like my students. I know I should know this, but I can't remember where I filed the information.
Yeah.
Good. Good. Okay, let's imagine that it touches pretty much exactly. So everybody, if you could stop with your work that you're working on right now, and let's come out of it for a second. So let's say I'm going to change the parameters. So you've had a chance to think about it, and I started you guys off in like variables, right? What did that feel like? Or what would it feel like for your kids?
Foreign language.
Probably foreign.
Yeah.
It's a little too much, too fast. Agreed? So like one quick thing. We all know about zone of proximal development. We knew about it at some point. We maybe still remember it.
Right.
There is one surefire way to get kids to shut down, and that's to ask them a question that's symbolic before it's concrete. Right? So let me go back a step. You all had access to some of this, and in fact, Donna's still working. Take it easy, Donna. So what I'd like for you guys to do now is just imagine if this is true. The distance across that circle is 1, and that's the same as the distance halfway across that square. What I'd like for you to do is real quickly just have a best guess. A number that's a pretty good guess about the distance around this thing, and write that number down. You're doing math still. It's just a guess. You have something written down, Nicole? You got to put it down. It's a commitment here. Sure. I know. So, my question, I'm going to guess that maybe a distance for this thing, it's about 12 things, units. How'd I do?
Terrible.
Yeah? Terrible?
No.
How'd I do?
Pretty good.
You feel like it's a good guess? How's it match with your guess?
Mine was 6.
What was yours?
8 and 3/4.
What was yours?
7 or something.
Wow. So, let me just do some quick thing. So, imagine if I had a class, okay? I could pretty quickly have all of them and this is what I love to do is the little sticky notes. All of them come up there and place their guesses here. And stack them up if I want. And find, if I really want to, I could probably find that in a good group of guesses. But here we got a small group. And so you guys all said like basically pretty small numbers, 6, 7, 8 compared to my number, which appears to be out here. So now the question is, who's the most right? So let's see if we can prove what the right answer is. Now Donna's already done some work, so let's do some work real fast. Take another stab at it. Another 30 seconds or a minute. Now we got 1 here. What's the distance around? Are they perfectly rocking?
Yeah.
That's so weird.
Is it not?
So we're only going to spend another couple moments on this.
You were closer.
I was?
That's what I think.
I'm curious.
So let me.
Oh, okay, I found the area. No, duh. Oh. Sorry. Yep. Yeah, you're right.
So we're not going to play this whole one out, but you guys can probably imagine where this starts going. So I have some convenient ways to think about this kind of work for a kid. One I have to remember. It's funny that Catherine did this, but in 5th grade, when kids are dealing with like perimeter and area, like basically they become the same thing in their brains, right? They have absolutely no clue what's going on. And what's interesting about this one is like my calculation process, which is a useful way of thinking about this mathematics, was to say, well, that's 1, 2, 3, 4, 5, 6, 7, 8. So I found 8 around the square.
That's what I did. It just took me a lot longer to get there.
How did I do it here then?
Well, you can flatten it out.
I could flatten it out, or I didn't do too much worrying. Like it turns out the perimeter of a circle, it's pretty much the perimeter of a square of the same side length, right? So then, so I got 12. So, I got a good estimate. And, like, actually it's, like, nice just to, like, get into that thinking space for kids. And then, of course, I have some calculations I can do, which I think hopefully you guys did, and you were able to say, well, okay, if I have this perimeter here, you were able to set up, what does that actually mean? Well, it means that value of my side was 2. And you got there probably, after you stopped doing area, you got there pretty fast, and you said, well, you know what, the perimeter of the square is going to be something like that. Right? And then how do we find the perimeter of circles? Sorry? Diameter 5. So that's, that's easy. So now we're somewhere. And now if we go to the kind of the bigger question is if this is A and that's A, like I'm not interested anymore in this problem. I'm interested in every problem. What's the formula for this now? What's the formula for the distance the robot travels if the diameter of the circle is A and half of the side length of the square is A? Everybody take a second to kind of do your own calculations. See if that's what you get or if it's different.
What was the question again?
If instead of knowing that that's 1, we only know that it's A, is there a formula that we can build ourselves to show us the distance the robot travels? So you can imagine in a classroom conversation, classroom conversation that we could have all sorts of, we could move from people who are thinking about it again in kind of a rote way. So let me just like hit what I mean there. It's like a student who was accessing this may have gone backwards and said, well, I have to go A plus 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 A. And that's okay. So long as they can get to the point where they can see it's that. Right? But a student who is maybe just one step above it, thinking about how these things work, would have first saw that whole total here was 2A and said, well, it's 2A and I need 4 sides, and now I have 8A. And that's whatever. It's fine. We got there. And really the pi times diameter is, we would hope, clicks. But maybe it hasn't already. So we just really need, like we had, that's okay. And then we have another version of it, right? Another, like, maybe a simplified version is that. Like it turns out, if you want a formula for the perimeter of this shape, the square with the circle corner shape, A times A plus pi will get you there. Which maybe it sounds silly, like we don't need that, right? That's not ever going to be on the test. But what's interesting about just a problem like this, if I think about setting up a problem, and I think about guesses and explorations down here, and I want to find what our average guess is, which, by the way, all of those things I could have done on a Google spreadsheet, the guesses, and I could have populated them in Desmos in a heartbeat, right? And I could find my average guess, right? I could find my maximum, I could find my range, my quartiles all in Desmos if I want. I could have a lesson that hits data and probability. I have a lesson that reinforces perimeter as it differs from area. And in fact, does a pretty decent job without a whole lot of extra effort of reinforcing how formulas work, how simplification of expressions works. So the question is, does this belong in a middle school classroom? Does it happen in the middle school classroom?
I mean, the thing for me is that you are an excellent questioner. Like, it's not just about putting a problem in front of them and say, figure it out. Right? It's like those questions, like asking your own questions, giving them a little information, asking another question. Like, I feel like that's also so integrated into that experience. And like, that's not one of the standards either. Like, questioning the hell out of your kids.
I love it. Questioning the hell out of your kids is officially the new standard. So one thing that I do want to say about that is we actually have, we have our math actions and processes, which are I think in so many cases ignorable. And that's a shame. But I'll tell you what's uninteresting. What's uninteresting is to solve a problem like this, where your kids say, what's the perimeter of a square? Of this square, even. They can answer that problem pretty fast, right? By adding it up or whatever.
They can't. Oh my gosh.
So let's.
Last week, build a fence. Build a fence, guys. What do you do to build a fence? You're going, build a fence.
So theoretically, a student who has access to the procedure, if a student has access to the procedure, there aren't problems that are interesting anymore about the distance around a square. Right? It's just plug and chug. So then how do we get just slightly out of that space? And I'm not saying I have the answer, but I'll say, if the classroom doesn't create opportunities, at least for most of these things, like it didn't. And this is like a harsh statement, but like I don't know that you taught math that day. And I've said, like, I think right here in that little shape where they all 7 overlap, that's a sweet spot, and it's hard to find. Okay, it's hard to find that spot because you got to make sure your kids are communicating mathematically. Which communication in mathematics only happens in a meaningful way if it is student-led. Teacher-led communication in mathematics goes like this. Today we're going to learn about this. Here's the definitions and the words that you need to know. Here's the formulas, right? We are bad at communicating in math, so it's actually our kids. And to Catherine's point, to do this well, what we really, really need access to is how to orchestrate discourse.
That's 2 books down.
So, this lesson. Is there a standard about this lesson? No. And maybe it's not the perfect lesson. I'm not saying it's the perfect lesson. It's just meant to highlight. In this lesson, we could make conjectures. Right? In a weird way, we can model. We could actually like play this out and like do a graph of this if we wanted to, right? That would help us predict all sorts of things. Like, what if the value of A is this, and so on. In a really interesting way, we get to generalization. And all the while, it's reinforcing procedural understanding about perimeter, building up conceptual understanding about how equivalent expressions work, because that's what's happening up here, is that once we see that all these things describe the very same thing, our students can have a sense of how that plays out. And if we're really careful about it, like just the part where I counted around was like an initiation into just mathematical reasoning that my students can feel comfortable with, and it builds their feeling toward mathematics that is positive. So what do I think is true about our middle school math standards? That you have to bundle And you have to make sure that I think it's possible. In darn near every single lesson that we have in middle school, you can do it from a geometric context, rely heavily on data and probability to be part of your classroom like sense-making experience, and then just try to reinforce the things that you care about with numbers and operations and algebraic thinking. Because I have questions here, like, so let's say now that let me go back. So we had an answer. So my question is, what's the value of A? If the robot travels, just for fun, I'll just say 30 feet. What's A? Now, there are all sorts of ways to process this. Like, what's a good guess? Like, what's a good way to guess at what A is right now? How would we think about that? Don't do too hard of math here, but what's a good way to think about what A could be?
Well, if I use the formula from the generalized statement that I had earlier, I would divide.
You do some division. And let me even go like even one step. So remember, my guess was just like it's just 12 A's around.
By 11 and 12, you get approximately 2.5.
The ability for this group right now to move pretty quickly to say it's going to be about 2.5 is probably why we're math teachers. Okay, and it's probably why our kids don't understand math, because sense making in mathematics is an afterthought. The first step in mathematics for most students is start doing the work, plugging and chugging, calculate. It's pen to paper or pencil to paper quickly. When in fact the sense making is pretty critical here. So we've had this exploration. We have an idea that it should be around 2.5. Can we prove what it is? And by the way, I say, everybody guess. Get out just another Google form. Everybody guess at what you think the answer is, and let's plot those sons of guns and see what happens. Why not? Because I'll tell you what's boring is doing data and probability at the end of the year. That can be a part of every week. I should have one problem where my students guess. Do you want to find out A, or you're okay with moving on? I said let's move on. What's that?
I wrote it down on calculator.
Yeah. So, and if you go back to the one that I like, that's this one. It ends up being a pretty easy problem to solve, right? It should be. By the way, the same problem is interesting if it's a shape like this. So you can imagine that. I think actually you could probably, if I'm imagining versions of this problem, I could do all sorts of versions where I have like equilateral triangles on it, if I could draw. Yeah. And it's just the point is like looking at the structure of the geometry here, which we want to reinforce. And geometry, in my opinion, especially in middle school, geometry is the best context for most of the work that you're going to do. So Catherine's already kind of played with this a little bit, but I want to ask a couple questions about how. When's our session over? 15? 25? Okay. So, Catherine, we kind of went into this already a little bit. So you may have some ideas that I need you to hold to yourself for a second, okay? I'm curious about whether or not we can create a graph that shows us the length and width of every single rectangle that has an area of 24. So the area of the rectangle is 24. And my question is, what are all possible side lengths of rectangles that have the area of 24? So think about this for a second. You do whatever you want. What are you thinking about? What? Perfect. Oh, this is good. This is good. Now, of course, we're talking about area here, so I just want to reiterate a couple things that we know about area. By the way, this is something that we're not, the challenge here isn't about area. It's about something else. So what do we know about area? Well, just so you remember, we were in perimeter a moment ago, so sometimes we can get confused. So area, we just need 2 bits of information, length and width. And what do we do with them? Right? No big deal. Okay.
Again, you're not in my classroom.
True. True. Which is why
I don't think it's a very big deal.
But if I was in your classroom, I would have done something different. I would have grid paper, and I would have said draw a picture of 5 different rectangles that have the area of 24. You know, or I would have had little square blocks or whatever. You know, some kind of tiling, some kind of manipulative, some kind of way that they can draw.
And it's not all of my children. There are
Yeah.
just those ones that you're just like.
All kids need a place to start.
Yeah.
And so when we're thinking about designing stuff, we got to make sure that if that place to start involves colored pencils and grid paper and a couple of manipulatives, it better be around. You know. Okay, so what did you guys? Where'd you start, Donna, when you were thinking about this?
Just listed the factors that could get you 24.
Okay, is that what you did, Nicole? Okay. Did you notice anything about the factors that you created? Anything interesting to you?
Well, as one side increases by 1, the other side is divided by 2.
Give me a specific case where you saw that happening.
Well, I could have 1 and 24. If the 1 increases to 2, then the 24 was half to 12.
So if I increase this to 3, then I would go half to this.
No, I just saw that on the first row.
Oh,
My kids.
that's okay. That's okay.
And then when they go to the second row, it doesn't continue to work. But they see those patterns in the beginning, and a lot of kids will see it once and say it's going to, Right.
Let's try it out. Now what?
If you divide by 2, you get 6, it won't fit.
So what's my answer?
It should be.
So what do I divide by? Sorry?
4.
Div.
You just have 3/4.
So it is 3/4 of it. So what do I divide by? It's hard.
I just took forever to do that.
We had to do some backwards mapping on that. Man, I don't know if this is going to be productive, y'all. What's here?
That's 4. So if you made your first one 2 over 1, your denominator increased 1.
Oh.
I don't know. Okay, let's try it. So what's this going to be?
So then that would be 5 points. If that pattern continues.
Oh gosh, what is 5? What's 5 divided by 5/4?
It'd be 6 divided, 6 divided by
24/5.
No, I'm just adding 1.
Wait,
Oh, I'm doing from this one?
So it's 6
Thank you.
24/5. 24/5. 4 and 4.8.
Okay.
Is that true?
Is that true? Is that right? So how would I check to see if this is right?
5 times 4 and 4/5 and see if you get 24.
So
It works. At least-
That's
Yeah, it
neat.
works. That works.
So what's, yeah, it does work. That's so neat.
And the number is the denominator, so now you can go to the infinite number. The number is the denominator, and the numerator is 1 more. Whatever your number is on the left side, so now if one side is A, you're going to have A, and then the other one is going to be 2A divided by A. Or, no, A plus 1 divided by A.
okay,
No, the
same.
number is the denominator. The 1 is the 1, and the 2 is the, you see what I'm saying? So the A would be the denominator, right? Wait, let me see. No, it's, well, it switched all of a sudden. The first two is the denominator, look. The first two it's the denominator, the second two is the numerator. So can you, I don't know if you can do the nth term yet off of that pattern.
Okay. What's this graph look like? Not ignore everything else over here. We've got these things here. Oh, this one's even hard to imagine. So let's just do that. We know this one. What's the graph look like of every single point that shows me that if I multiply two numbers, I get 24? What's that graph look like? Take a second to think about it. Look, you have these numbers here. Sketch it if you can. Yeah, sketch the graph. By the way, we did just create a recursive formula, but it's a challenging one. It's a lot different than I think what we normally handle with recursive formulas. Do you guys have an idea? Do you have a sketch of what it's going to look like? Make sure you have something written down before we move on. So there's a couple things that I can do on Desmos, and this goes back a little bit. There are a couple things that I can do. In a classroom conversation where I'm having this discussion, now if my computer's this far away from my my whiteboard,
then it's not going to work.
it's not going to work. But in Desmos, it's perhaps, yeah. So what's nice is I can come over here and I can make points. So did you see how that point just came up here? And we've got points that we can deal with now. 3 and 8, 4 and 6, and I think the last one that we did was 6 and 4. But you know what? I'm kind of on a roll, and I notice right here there's some symmetry. So let me just come down and do 8 and 3, 12 and 2. Everybody's okay with all this? There we go. Does that look right? So my question is, okay, is that what we thought it was going to look like? This little curvy thing? Who thought it was going to be a curve, or did you have kind of a line going?
I had a line going.
Okay.
Because I stopped.
Okay.
So
So initially it was starting to, if we came back,
the first 2 or 3 looks like you're going to have a line.
right? If we came back and we just did those, I could make an argument. I could especially make an argument that it could be a line here. It is a line. It's only 2 points, so we'll ignore that for a second. So now my question. What is the equation of this graph? What I'd like for you to do is take a second, maybe 30 seconds. Try to come up with a couple ideas about what the equation to this graph might be. Whatever you do, don't look at a calculator or your neighbor's paper. Okay? 30 seconds.
Did you go this far in middle school too?
Oh, yeah. Oh, over here?
Oh, no.
Everywhere. I would do all of this.
Oh.
Yeah, this is 7th grade here. This is reinforcing 6th grade division and multiplication of fractions. I would definitely use it.
Do you call it like a rational function or
No.
no?
No. When we get there, we'll only refer to it as what?
Okay.
Oh, yeah.
Whoops.
They don't really have access to rational yet. Like they're just learning that rational numbers exist in 7th grade. So.
6th grade, no. 6th grade we talk about rational numbers.
Which,
Or maybe I do because I teach 6th grade.
Yeah.
We do it all together. But I really thought that the first unit was rational numbers. Or the first.
Let me just double check.
I really thought that.
Yeah, positive rationals. Okay.
Yeah, positive rationals.
Yeah.
I really thought that I.
We don't. So kind of one of the things is that we start calling them rational numbers, but it is not. It is not really in the depth that we go on later.
Oh no.
So.
That's why I said whenever I'm doing it with my 6th, 7th, and 8th graders, we do a little chart and we talk about rational numbers, and I even throw in, irrational and
Okay.
that type of stuff.
Well, that's what I was going to say. Is I think rational is hard to, fractions, decimals, all this stuff. The point here about rational is that it's not a whole number. But since we don't really get into, we don't go into pi, and I'm pretty sure I'm right about this, until 7th grade. Does everybody agree with me on this?
What was the question? I'm sorry.
Pi,
In 6th grade?
I don't think we do pi until 7th grade. Yeah. So one of the things that I'm cautious about is, so for a student to understand what rational is, they have to actually understand what it is compared to what they've done. So we really need to distinguish it clear that rational numbers can exist in between integer numbers, whole numbers. That's the first thing. And then later on, we have a new thing that says, and irrational numbers can exist between rational numbers. Also, rational numbers do, but then irrational numbers not only exist between them, but cannot be defined by the rational numbers. And we have to really pay close attention to that progression because they can't explain the difference between rational and irrational until they've effectively understood the difference between fractions and, integers and rational. Were you able to get a graph yet? No worries. Let me take a quick moment to reflect. What about as an adult? Did you get somewhere as an adult?
No, I didn't get there. I started
play with the kids this time just to be able.
Okay. Yeah, I'm pretty okay with you thinking about it with all your mathematics. Let's talk about things that we know are true about this. Like, what are these points? What do they represent for us so far?
On the graph, there were pairs.
Okay, we'll take both. Good opportunity here, by the way, for establishing common definitions and common terminology for our math classroom. So, okay, coordinates, ordered pairs. What else do they tell us?
As one increases, the other decreases.
Yes, we definitely found that one out. That was helpful.
We know for sure that they have to be multiplied together and be 24.
They have to be multiplied together to get 24. That's how we came up with them in the first place. So for every value here, I multiply it to the value here, and I get 24. Put that down in an expression or an equation real fast. Don't worry about the function. Don't worry about the graph. Write down what Catherine's saying, and I revoiced. What did she say? Is that what you were thinking, Nicole?
Yeah, but I mean, I was actually thinking writing that before she just said that.
Why didn't you?
Well, because then I
Is that too simple?
then I started thinking, okay, well, I want to write this.
Yeah.
So I was trying to get.
You were trying to put it into some kind of form that was a y
that's
equals.
where I was trying to get before I wrote down that.
Yeah, totally. Do you guys think that's the right graph, though? Let's see. So I'm gonna just try it. I'll just type it in as exactly as we have here. What do you guys think? Seems to go through all the points, doesn't it?
Mm-hmm.
That feels pretty good to me. Now, there's also all sorts of things that we can explore here, but I just wanted to get to this point to make a couple conversations clear. Like, middle school math is harder, and it's harder for us probably, because frankly, the way that we look, like whenever I looked at middle school standards when we did our revision, what I saw was a lot of rules about how math works. And what we try to make sure happened in our standards is that the focus was about how the math works. Not the rules, but just like how. Like, what does this mean? And like, frankly, if I had to say what altogether matters in middle school, I could summarize it by saying they better understand integers and operations around integers. Probably they should be mastering fractions and fraction operations. That's middle school. That's 6th grade. Which, by the way, it's incumbent on our middle school teachers now to make sure that they absolutely never again leave doing work in fractions. They are the reinforcer of that. But there's one thing that matters the most, and it's proportional and indirect variation.
Mm-hmm.
That's it.
Massive in seventh.
It's it. It's all that matters, in fact. So what is inverse proportionality? It turns out it is just cases of squares that have the same area, rectangles that have the same area.
Right.
That's how it works, and it can be applied in all sorts of scenarios. But if a student leaves 7th grade and doesn't have a sense about that, they may be missing out. I almost guarantee they're missing out on something. Because now we have an opportunity. We have an opportunity to say to ourselves, I can think about problems like this now. Right? And now I can also, if I want to tie this back to other things I should be caring about, what if I asked you guys for the perimeter, the formula for the perimeter of every single rectangle that has the area of 24? What would you do for that now? It's actually, well, you want to try it? Just real fast. What's the area? I mean, excuse me, what's the perimeter?
And it's for 24?
Yeah.
Of a rectangle.
Of a rectangle. That equals 24. And now, importantly for me and all the things that I'm interested in, even though it can be much later, did you get x plus y equals 12?
About 2x equals 24.
Did you find out by 2?
Yeah, you know. There's that way too. If I just take what I've just done, I have another question for you. Do you see this? First of all, to me the straight line that I just graphed that's black, for whatever reason always feels curved. Whenever I look at it, it feels like it curves. Does it for you guys, or am I just crazy?
I can see.
It feels like it bends because it's dealt with.
Yeah.
So my question for you guys is, they intersect here and here.
What does that mean?
And what does that mean?
That means that.
Now, no, we can
And
figure
those
it out.
2 points, they have the same area and then the same perimeter.
That with those, these 2 points, which happen to be the same, they're symmetrical. That we have a very specific type of rectangle, which maybe I would like to call the truest rectangle. The truest 24 rectangle is one that has a perimeter of 24 and an area of 24. And it's made up truest. But imagine being able to have a student explore what these things mean together. And by the way, is our intersections of lines middle school? You know, maybe. Yeah, 8th grade.
Yeah, it's 8th grade now.
But guess what? It doesn't matter. Like, I didn't have to calculate anything. So the point wasn't here, even though it could happen. The point wasn't that I had a student looking at this and saying, oh gosh, well, let me write it back in a form that we can handle, since I can set them equal to each other. I didn't have them do this. Now solve. Oh man, yeah, that's hard. That's not my point here. My point is what's happening in mathematics. What's we're spending time on in the middle school classroom? Bundled connections, vertical connections, paying attention to geometry, paying attention to statistics. 6th and 7th grade mathematics are too hard to teach if taught as a checklist. They are too hard to teach if you think in a day you're going to do 20 problems each day. It's too hard. In fact, I think it's probably too hard to teach if you think you can cover all the material by the time the test happens.
Especially in the checklist.
Especially. I love the point that you made, Nicole. Students need to experience these things multiple times, and that's one of my most fundamental beliefs about middle school math right now. Is the very worst thing that we could do is teach one thing and leave it forever.
Yes.
It needs to come back in multiple iterations, and just like you're saying, and especially for our students who have struggled in mathematics. Oh, this lost me. You're still recording?
No, it stopped it. Yeah, the battery might have died in the mic. It's not on.
Yeah, looks like it. So, I got distracted by that. So what is it that we do in these classrooms? I think in all classrooms, but especially in these. For our middle school kids, they better see that mathematics is something that we can play with, not just memorize. It comes down to that. Because I'm pretty sure middle school is hard enough anyways to have to memorize a whole bunch of pointless things.
Poor middle school kids.
Yeah.
They're just going through so much horrible stuff.
And by the way, you know what will never ever be on our state assessment? Is finding out the measurements of the truest rectangle. We won't do it.
Right.
Why not? It's too fun.
Yeah.
It's too interesting. It's too unfamiliar.
Could your big question also be, is it possible for a rectangle to have an equal perimeter and area?
Oh gosh.
That's
If we got,
I was like,
if we got to the point of this, and we felt good about it, that as the next question, as the challenge question, that's what we're spending a day on. Yeah. Which, by the way, it just takes me back to a whole other point that I was talking to Christina. Catherine.
Right.
You know, most of the same letters. It's very organized. To Catherine about is, what the heck is this anyways? What is x plus y? And it turns out it's the graph of the number bond. So just like our previous graph was the graph of all the factors of the area, we can actually do a graph like that, and it's the number bond. So every single pair of numbers where we add them together equals 12. So now just like, think about mathematics that way. And so like slope isn't just this rate of change thing.
Right.
And these words have context, because actually you'll notice that not a single thing that I'm paying attention to here is about slope.
Right.
It can be about intercepts, that's one point. I could talk about intercepts.
And why the 24?
And
I like the 24 one, doesn't have any. That's my interesting question.
Yeah, the area one?
Yeah.
So the fact that the area one, so where does it cross 0?
Never.
And why? Right? Make a claim. Defend your claim. You know what I mean? I think that's math worth doing. And like I said, this won't ever be on the test, but if I spent 2 days on this, I think that my kids are going to have a totally different experience with thinking about relationships between numbers, and especially relationships between numbers like this. And they'll think about covariation differently, which, by the way, is all that we do in high school is covariation. How do two things change together? All right. So what do we figure out today? Would you just take a second to reflect, think about what have we done, what have we accomplished, what does it mean to you in your classroom, if anything?